In this video, I will show you how to solve the bin packing problem by implementing a model, a mathematical model in Python and Gurobi. This video is based on Anaconda Python and Gurobi Optimizer. The versions that I'm using currently are Anaconda version 2019-07 with Python 3.7 and Gurobi Optimizer versions 8.1.1. And you can see how to install those packages on the screen now. You can pause and install if you like. So the bin packing problem, in the bin packing problem, for short BPP, we are given a set of n items with weights wi for every item. We will index from 0 to n-1, just to be consistent with Python indexing. And we are given an unlimited number of bins with identical capacity C. And all parameters are integer, positive numbers. And the problem is to assign each item to one bin, so such that the total weight of the items in each bin does not exceed the capacity, and the number of bins that is used is minimized. So to compare it to a knapsack problem, for example, the knapsack problem, we were maximizing the profit from a set of selected items that we were packing into one knapsack. This, in contrast, is something like we have multiple knapsacks, and we need to pack all items, so we don't care how profitable they are, we need to pack all of them anyway. And but the problem is now, if we don't pack them carefully, we can use many knapsacks or many bins. In this context, they're called bins. And so the problem is to pack them in such a way that the number of used bins is minimized, and obviously that means we need to pack them in such a way that we utilize the space in each bin very well. Now, the problem might seem easy. We could just start from the first bin, pack as much as we can in it, and then move to the second bin and so on. But if you do this, if you pack bin by bin, you are actually very likely to get a solution that is not optimal, that will use maybe more bins than necessary. So it's not an easy problem. An example application could be in shipping. You know, imagine you have these items, you have the dispatcher of a cargo that has to pack packages, and all that he has to care about is weight. So imagine these are small but heavy items. So in terms of their shape, they can fit in a container easily. It's just that they are quite heavy, and we don't want to overload containers which have maximum weight C. And so, the problem is, of course, to pack in the minimum number of containers such that the weight packed in each container does not exceed capacity C. So here you actually can see I did a few imports, pandas and NumPy packages, and then also Gurobi Py package to be able to use Gurobi Optimizer. And I also have defined here a set of instances. So just to be clear, each line in this list here defines one instance. They are actually taken from standard benchmark instances for the bin packing problem. So this is just the name of the instance. And this is capacity. So you see the bins can be loaded with up to 150 units. And then these are the weights of each unit. So the first unit 0, has, or item 0 has weight 98, the next one is 93, the next one 92, and so on. And just to not to make this document too long, I did not break the line, so you can actually see that it goes on. If you scroll to the right, you will see these numbers go on, and actually the last instance has quite a few items. So here's a little bit of code here to display it. I actually convert the data to the data frame, and then calculate something like n number of items, minimum, maximum weight, and then apply a lower bound. So if you run this code, you see that we actually have 9 instances, numbered 0 to 8, with from 60 to like 1,000 items in the largest instance. So remember, at the time, we will be solving just one instance. And the interesting question first is, what's the lowest number of bins that we will need for sure, right? Obviously, we will definitely need at least one bin, we could have said, right? So this is a lower bound. Let's implement a better lower bound here. So what is the lower bound? The lower bound is something like a guarantee that we can certainly not obtain a better objective value than this number. What is the minimum number of bins that we know we will need for sure, let's say for this first instance? So one way to approach this is to assume that, instead of packing each item in exactly one bin, we could split each item into more than one bin. So we could have fractional packing. And in that case, we could basically pack, let's say, in this instance, 98 units. The first item goes into the first bin, and then part of this 93 goes to the first bin, such that we fill up the capacity 150. And the remainder goes to the second bin, and so on. We do this, right? Packing, if the item doesn't fit fully, we pack part of it and into the bin, and then open the next bin. This is, a linear relaxation. This is a fractional relaxation of the bin packing. And actually, in that case, how much are we going to use? Well, we are going to use just, if you add all weights, it will give you the total weight to pack. And if you divide this by C now, this is going to give you a number of bins, right? So for example, if you calculate this, you're going to see, let's say, a number 21.7. Well, if you get a 21.7, that actually means we need at least 22 bins, because if you need 70% of one more bin, then that means we need that bin fully, right? So this will mean 2. So I'm actually going to round this up. To round this up, you can use math ceiling function, okay? And so we calculate the sum divided by C, round up, and that should give us the minimum number of bins. And I'm actually going to convert it into int just to be on the safe side, right? So you can actually, this is one of the trivial lower bounds. There are other methods for calculating lower bounds, but you can read research papers about calculation of lower bounds. A lot of papers have been written just for this problem. So if we run this again, now you see the last column here actually shows lower bounds. So you see our first instance, we will need at least 22 bins. I don't know how many. The interesting question is also, what's the maximum number of bins we may need? And one trivial upper bound is n. If I have 60 items, and each of them obviously has to fit in a bin on its own, that means maximum I will need 60 bins. So somewhere between this and this, there is an optimal solution. I don't know what it is. It might be that the number of bins I will need is 60. It might be that it's less. It might be that actually it's 22, but definitely not less than 22. And the optimal solution cannot be less than 22 because we calculated something that proves less than 22 is impossible. And the optimal solution is certainly not going to be more than 60 because we know there is a trivial solution to pack each item in a separate bin that will give us 60 bins. So I'm going to try and model this. Now, before we start implementing, let's look at these lines. This is just extracting the first instance number 0 from this set, taking its name, taking its capacity and weight, right? The weight, weights, the list of weights, and then calculating n from it, calculating the lower bound using the function that we defined earlier here, this function, lower bound, and setting the upper bound equal to n. So if you run this, right, we see we have an instance with capacity 150, with 60 items. I'm not displaying the weights because they take too much space. And with lower bound 22 and upper bound 60. And this is what we would like to solve now. So if I want to solve it using an optimization model, what I need to start with is obviously create a model, right? And again, I'm going to call Gurobi function creating the object model. And again, as in other videos, I'm going to set 2 parameters, log2 console, let's say to true, and time limit 60 seconds. Right, so this is seconds. And now what we need to define is we need to define the decision variables and objective and constraints. But before we do this in Gurobi, we need to think about modeling this mathematically. So how would we model this problem mathematically? So let's go back to our decision problem and think about how can we model this mathematically. So I'm going to create again another cell, change it to Markdown, and write mathematical model of the bin packing problem, right? So first of all, we need to allow all possible solutions. So for that, we need to actually say that every item could be allocated to potentially any bin, right? We're going to assume that we have n bins, n items, and we don't know how many bins will be used, so we have to assume some kind of upper bound number of bins. So for the time being, I'm going to say that n is number of items, and I will say something like UB is maximum number of bins, right? But in fact, UB will be equal to n, right? Because I have no better way of estimating the largest number of bins. Maybe later I will devise one, but for now I'm going to just keep UB equal to n. Remember that I could use just n for both, but for the future modifications I prefer to refer to the number of bins, potentially maximum number of bins, as UB, so that I can later on try and reduce this number. So how can I model this using mathematical programming? Well, I will need to define decision variable, a binary decision variable that will say, so variables will be x, and I'm going to put two indices, I and j. And this binary variable will be 1 if item I is assigned to bin j, where I equals 0, L dots means lower dots, 3 dots, and up to n minus 1, and UB equals 0 up to, sorry, not UB, j equals 0 to UB minus 1. Right? So what does this variable say, right? I should probably say equals 1 equals 0 otherwise. Right? So what does this variable say? It says if item I is assigned to be j, then this variable is equal to 1. If it is equal to 0, then item I is not assigned to be j. That means it has to be assigned to another bin. I don't know which one, but there will be, for another value of j, there will be a value 1. Right? So the decision variables, notice the way they are defined, they allow for any possible assignment. I'm not, again, restricting an assignment to something like, oh, I know item 1 will be definitely in bin 7 and item 2 definitely in bin 5. I cannot do these restrictions, at least not many of them, without maybe preventing the solver later on from finding the optimal solution. I have to allow for any possibility, right? So this definition of variables does allow for this. And now I need to define the objective. Now the objective is actually hard to define using Xij variables because what I need to minimize is the number of bins used, and actually this is not that easy to define, to minimize just using Xij variables. There are ways to do it, but I'm going to omit it for now. And I'm going to focus on the constraints. So let's leave objective, right? Let's say to do, and then we do subject to what constraints? Subject to, and the constraints will be, well, I need to assign every item I to exactly one bin. So I need to say, I need to look at variables x, ij. These curly brackets ij are there. If you forget about them, look what happens. The formatting, I is an index, but j is no longer an index. It's like an X symbol. If you put this in curly brackets, both of them are used as indices. So what I need to do is xij, I need to sum xij's for every bin. If I fix, if I fix item I want to see if it is in any bin, right? The variables that refer to any bin for a fixed item I, the sum of those has to be equal to 1. So I'll have to do 0 to ub minus 1, xij equals 1. And I'll have to do this for every item, I equal 0. Actually, I can use again this from here. Right? So what does this mean? Take item 0. Look at this item 0 and all possible j's, meaning all possible assignments of item 0 to any bin. Add all variables. Exactly one of them has to be equal to 1 because we're saying that this item has to be assigned to exactly one bin, right? The sum cannot be 0. It would mean that the item is assigned to 0 bins, so it's not going to work. And the sum cannot be more than 1, for example, 2 or 3 or 5, because it would mean it is assigned to more than one bin. We need it exactly in one bin. Okay, that's one constraint. The other constraint is we have to make sure what is assigned to every bin does not exceed capacity. So this constraint, I'm going to write it kind of backwards. I will say for each j, for each bin, right? For each bin, let's put a comment here. Item in exactly one bin, right? So for each j, for each bin, right, total weight in each bin has to be less than or equal to C. So this is LEQ command C, right? I need to calculate what's packed in each bin J, and then I have to make sure that what's packed there, the total weight of it, is not exceeding C. So I will have to take the weights, W, and multiply them by the variables, right? And do this. So I will have to take W I weight times X ij. If the item I is packed in bin J, then its weight enters the total weight in this bin, and this cannot exceed C. But of course, we need a sum here, right? Because I need to check for this bin J which items are packed. Well, I have to go for all items I equals 0 to n minus 1, and I have to make sure when I add for all items the weight that it contributes to the total weight in this bin, right? And it will contribute, if X is 1, then it is packed in this bin, and then the weight is added here, right? And the total weight of those items that are packed in the bin must not exceed C, right? And the last thing, obviously, that we have always is Xij in 0, 1, which means Xij is binary, and we need it for I equal 0 to n minus 1 and j 0 to ub minus 1, right? So we have our constraints. These constraints, I think, are complete because they say every item has to be packed exactly in one bin, exactly once, and then the total weight in each bin does not exceed C, but we still miss the objective, right? This will give us a feasible solution, but not necessarily optimal. Now, for the optimal solution, we need, the easiest way to model this is to define additional variables. You see, it would be a good idea to know if the bin is used or not. And it's hard to guess because, right, from the X variables, because there are many variables referring to bin J, right? Exactly n variables. And if any of them is 1, then bin is used. If all of them are 0, then bin is not used. So there are too many variables defining this information. I can actually define it using one variable. Let's call it yj. We could call it anything, but right? And then let's say yj equals 1 if bin j is used, and then equals 0 otherwise. So if it's not used, right? And this variable is for j, I forgot a dollar here, sorry. For j equals 0 to ub minus 1. So the variables are yj equals 1 if a bin is used, 0 equals 0 if the bin is not used, right? Now with this, the objective becomes easy. So the objective becomes simply minimize sum of, for j equals 0, I need the curly brackets, to ub minus 1, yj, close, right? And this is number of bins used, right? So this looks easy, but it's not yet complete. Why? Because first of all, the objective does calculate what we want. If 1 means bin is used, 0 means not used. If you add this, you will have the number of y variables that are equal to 1, which is the number of bins used. However, now the y variables are completely disconnected from the x variables, right? We can set x variables to something. We pack items in some bins, but then we can set the corresponding y variables to all to 0. Why? Because there is nothing forcing them to become 1, right? Actually, we need a constraint also here. We should add another line that y variables, yj, actually small y, are binary, and of course for only index j, right? But now we also need to make sure if an x variable is 1 for a particular value j, then the y variable has to also be 1, the corresponding variable for the same j, right? And so this is a constraint that actually one could add something like this. We could say that xij is less than or equal yj, right? We could link it like this. If xij is 1, then y has to be, for the same value j, has to be 1, right? For any item, if it is packed in a bin, then the corresponding y value is 1. That would work. However, that is actually a lot of constraints, and this expands the model a lot. There is an easier way to do this. If you notice that multiplying c here by yj will do the same job, right? Because if I now go to this constraint where there is less than or equal c and then multiply the c by yj, I want you to notice that, right? What does that mean? It means that the capacity of the bin, the total weight in the bin, is c times y, c times yj. So what does that mean? It means that if y is 1, then actually we have capacity c, and then we can pack up to this capacity c. But if y is 0, then the capacity is c times 0, which means 0. And because all weights are not 0, they are all positive values, all variables x have to be 0 if this is 0, right? So this actually serves as the linking, and this constraint is no longer necessary. So we can actually completely drop it. So I can delete this linking, and this model is sufficient. So we have two types of decision variables. Xij is the bin packed, is the item I packed in bin j, and yj is the bin j used. We minimize the sum of yj's. We make sure every item is packed in exactly one bin, and then we ensure this constraint, total weight in each bin, is limited, and let's say also linking xij with yj. This is also linking xij variables with yj, right? Okay, so this is the mathematical model. And let me stop here, and I'll record another video. I will have another video for the modeling this in Python and Gurobi.